Hello everybody, this is Dr. Ali Mughebel, and in this video we cover Gram-Schmidt Orthogonalization Procedure. For more resources, slides, and what have you, please visit our website and YouTube channel for additional resources. The outline of this video goes like this. We'll start with the Gram-Schmidt procedure, we'll look at some examples, and we'll look at signal constellation. So we'll learn how to construct the basis for a given set of signals. So this signal can be generated using the basis, and we can get the coefficient. So the Gram-Schmidt orthogonalization procedure is a technique. It's a technique to find a complete set of orthogonal functions. We will be given signals, we have capital M signals, and they're all energy signals, and we need to find the basis for these signals. So the first base is to select the same first signal. Of course, the order would be arbitrary. We take the first signal to assume it is our first base. But we need to divide by square root of E because we need orthonormal. This has to be normalized. So the signal itself could have an energy which is more than 1. So we need to normalize this. How do we do this? By dividing by square root of E and not E. Why square root of E? Because this is the amplitude of the signal. And remember that the energy is related to the square of the amplitude. So the amplitude itself will be divided by square root of E. Alright, so EI in general is the energy of signal SI. So E1 is the energy of signal number 1. We can resolve this equation vice versa, saying that the first signal would be square root of E1 times the first base. So we get S11 as square root of E1. That's the first base. It's simple. Take the first signal and normalize it. Let's move to the next base. Now we'll take the second signal. Similarly, I will take S2, and I can find how much of S2 is already in our first base. So we'll project S2 into phi1, and we get S21, which is a measure of projection of how much of S2 is already in the first base. We'll get that one. And now we'll see how much residual we have. So we define an intermediate function, G2, which equal to the second waveform minus how much is already presented in phi1. So we'll get S21 times phi1. If we get 0 out of this, it means there is nothing new in S21. Everything can be represented with phi1. Otherwise, we'll get some residual. That residual is known as G2. Now, to make sure that G2 and phi1 are orthogonal, we have removed all the contribution of S2 into the first base. Now we can proceed in the same way. The remaining of this, which is of course orthogonal to S1, to phi1, is G2, and we need to normalize. So I'll find the energy of G2, which is the area under the square of the curve. We take the square root because this is the amplitude of the signal, and we get the second base. So the second base simply is how much in the second signal, which is not represented in phi1, take the remaining and normalize its energy. So G2 is the difference between S2 and what was already represented, and we can find the energy one way or another. Of course, now by definition phi2 will be orthogonal to phi1. We can show this. We can substitute this term in phi1 and do the integration to show that the answer is going to be 0. I'll leave this as an exercise for you. We can continue in the same way, go into S2, S3, and S4. So to generalize, I will just write that Gi, the intermediate function before normalization, would be the current signal minus all the previously represented signals, and this is why we have the summation from 1 up to I minus 1 up to the previous base. So we remove all the represented signals in phi1 and phi2 and what have you, and the remaining will be Gi. This Gi would be normalized. Of course, once we can find all the projections by projecting on the previous basis. So Sij, as we know, is Si times phi j. This G has to be normalized, so we'll find its energy, we take the square root, and we get the next base. That would form an orthonormal set of bases. With this, we can look at some examples. Remember that the dimension n is less than or equal to the signal m. N is the dimension of the number of bases, and m is the number of signals. So if these signals, of all the signals, are linearly independent, they are independent, which means we cannot represent them. They are not related. So in that case, n would equal to m, right? But in general, if they are not linearly independent, we get n is less than m. All right, because some of them would be related. The intermediate function d is 0 for I greater than n. So if you continue more than the number of bases, of course, all the functions would be 0, and this is why we don't need additional basis functions. Look at this example where we have the following 4 signals, which are represented by one base. And if you recall from your communication background, this is an example of A is K, amplitude shift keying, where we have the difference between, we have all the same base, but the difference is the amplitude. So one signal will be 1 times phi, minus 1 times phi, 3 times phi, and minus 3 times phi. This example, if you recall from your communication background, we have 4 possibilities. That's capital N equal to 4 and N equal to 1, only because we have one base. We can send 2 bits using these symbols. Okay, that's log base 2 of 4. And usually we use gray coding, where we represent the bits, for example, here like 0, 0, and then we have 0, 1, and that's 1, 1. We don't go by order of binary 0, 1, 1, 0, because otherwise, if you do this, if you say this is 1, 0, then a mistake here will result in 2 bits in error. The first one will be different. So when we go from 1 to a next closest item, we try to make sure that there is only a minimum difference of bits. So if you say 0, 1, and 1, 1, that would guarantee that we have only one bit at a time. That's called gray coding. I'm sure you have seen this before. I'm just recalling. If you are not sure, you can search for gray coding. Now let's do a full example where we have, I will leave you with an exercise, but to look at this example, use Gram-Schmidt procedure to find the orthonormal basis functions for the set of signals. We're given 4 signals, S1, S2, S3, and S4, and we need to find the bases. So let's do the procedure. It's not about memorization, it's a concept that makes sense. So the first base will be the first signal, but it's normalized. How much is this energy? Energy is the area under the square of the curve. If you square 1, you get 1. And the area now becomes 2. So this is not normalized. The energy here is 2. So this has to be normalized. We divide by square root of 2. We get the first base. Let's do this in a slower mode. Okay. So the same example, I find the energy of the first signal. It turns out to be 2. You will need to see the signal in a second to recall. So the first base, that's our original signal. The first base will be the first signal divided by the square root of the energy, which is 2, and I got the first base here. This is 1 over square root of 2 to make sure that the energy equal to 1. If you square, that would become half times 2, which is equal to 1. Now, for the second signal, for the second base, I will take the second signal and project it on the first base. And I got an area equal to 0. Okay. For the intermediate function, we will subtract 0 out of S2. What remains is S2, which means that S2 is another base function, but needs to be normalized. So its area equal to 2. So the second base will be the second signal, and we have to normalize it. So if you square now, you get 1 times 2, the area equal, you get 1/2 times 2, which is 1. So these are the 2 bases. If you just want to recall how we got 0 here, if you multiply these 2, you get positive times positive, you get positive area. Same area, but with a negative sign, cancels out when we got 0 here. Now we are having 2 bases. Let's see if we have more or not. I'll take the third signal and project it on the first 2 bases. Okay, here for simplicity, I'm just reproducing the signals, the 4 signals, and with the 2 bases. The third signal, when projected in S1, on phi 1, I got 0 because we have positive and negative cancels out. If I project the signal on the second base, S3 on this one, I'll just get a minus sign, minus square root of 2. Now let's see how much residual we have. So this signal, in fact, if you notice here, it can be completely represented with this waveform just by, there's a minus sign, it's just flipped version. So there is no wonder that there is no need for a new base. So if you take S3 minus S32 times phi 2, you get 0. The remainder after representing or projecting S3 on phi 2 is 0, because this is fully related. So I can continue. There is no new bases as a result of S3. Continue with S4. Just by inspection, you can see that S4 is made of phi 1, but with a scaling factor, which is minus square root of 2. Of course, the projection on phi 2 would be 0. If you take this and project it on phi 2, we have positive, negative, cancels out to 0. And we can continue in the same way. That will terminate the process because the fourth signal is fully represented by phi 1. And we got no intermediate function, and we have just two bases. Now, to continue with the example solution, we have seen that we have the three signals. There are only two orthogonal bases to represent the signals, the four signals up to 4, and we got n which equal to 2, which is less than m. If you want to represent this on the constellation diagram, then the diagram is made of a 2D diagram because we have two bases, phi 1 and phi 2. Now, each one of these signals will be represented as its projection. So we got square root of 2, square root of 2, minus 2, and minus 2. It's your job to find which is which. So basically we have S1, S2, and then we have the remaining signals, S3 and S4. Okay, now let me leave you with this example. It will take you a time to do this example, but also it will make sure that you understand the procedure. So please take it seriously, pause the video, or just finish up with the video and then try to solve this on paper and pencil. Remember, you cannot understand by using your eyes and ears. You have to do things with your hand. The figure below displays the waveform of three signals. Using Gram-Schmidt procedure, orthogonalization procedure, find an orthonormal basis for the set of the signals. Not only that, we need to represent the three signals in terms of the basis functions as we did in the previous example. So we need to show them as vectors in the signal space diagram. So 1, 2, 3, by inspection, maybe you can tell how many bases we can have, but then you can come up with the bases. And then once you come up with the bases, you need to draw the signal space and represent these three signals as point in the space. If you can do that, you will be in good shape. Remember that here, this is generic in terms of t. So when you normalize, you will get something related to capital T and the amplitude. That would be perfectly fine. Okay, we'll stop it here and we'll see you in coming videos. We'll be using our understanding of Gram-Schmidt procedure, our understanding of Gram-Schmidt procedure, our understanding of signal space analysis, signal space and vectors to do the analysis for the performance of communication and wireless communication systems, and to see which one is better in terms of performance. See you then.